Good day, class. My name is Engineer Steven. So I'll be taking you guys physics. This physics is particularly both for 100 level in UNIBEN and also for 100 level in delsu University of Delta State. So the scheme of work, they are somehow interrelated, so you can also use this to read when you are having issues. So for today, I will be taking you guys physical quantity. I'll be in the first part of your physics textbook. I will grant you guys up on that part. So let's begin. So first of all, the definition of physical quantity. What are physical quantity? These are the measurable parts, or rather these are quantities that have measurable physical properties. Physical property of a substance, which we all know already, is the size of the substance, the amount of the substance, or rather the size of the substance, the density of the substance, and all those stuff, the shape of the substance, the physical property of that substance, the durability, and all those kind of things. Then the classification of physical quantity. Physical quantity are classified into two. They are divided into two. Basically, the fundamental quantities and the derived quantities. So the same physical quantities, they are furtherly divided into two: the fundamental quantity and the derived quantity. The fundamental quantity, these are basic quantity. They are the basic or the universal quantity of all other quantity. All other quantity or all other measurement, they are gotten from this standard quantity, and they are usually represented. The fundamental quantity, examples of some fundamental quantities: include the mass of substance, the mass measured in kg, our length measured in meter, our time measured in seconds. Apart from these three standard ones, there are some other fundamental quantity that we have. We have the current, our current measured in ampere. This is the SI unit of these quantities. Then we have the amount of substance, measured in mole, the thermodynamic temperature measured in Kelvin. So we have this. This one is the Kelvin, thermodynamic temperature measured in Kelvin. There is also one, the luminous intensity measured in candela. So if you are not trying to do it dimensionally, or rather the way they represent their basic interpretation of this fundamental quantity is in this form, the basic interpretation. For the mass, it is measured in, you write m, or rather you write m. If you are trying to interpret it, the short form for interpreting the mass is m. Then for the short form for interpreting our length is meter. Rather, sorry, the length is the short form for representing it is L. Then our time is represented as T. For our current is represented as I. Our amount of substance, the short form is mole. For our temperature, Kelvin. is also T. Then candela, our candela is also C, or rather Cl or something like that. Candela, let me write it here. Candela, or rather the luminous intensity candela, Cl, any format you just put in mind, you can also use it to write it. Then for the derived quantities, they are formed from the combination of two or more fundamental quantities. The derived quantities are formed from the combination of two or more fundamental quantities. Example is our velocity, our acceleration, our force, our velocity, our acceleration, our force, what is that one? Let's say, okay, our density. These three is okay. Let's just fix on this first. So the velocity is our displacement over the time. Our displacement is also the same thing as our length from our fundamental quantity. Is also referred to as the length, and the short form for us representing the length is our L over our T. Then the acceleration, our acceleration is velocity over the time. And remember, we have already gotten our value for velocity here, so I can just write it here, L over T divided by T. And if you are to go further on this, it will give you LT raised to power minus 2. Then for the force, our force is equal to the mass times acceleration. And I told you that in our fundamental quantity, the short form for representing our mass is M. The short form for representing our mass is M. And since we are already given our acceleration to be LT raised to power minus 2, I will just place it here. So these are the way we represent the derived quantity for a particular function or something. So let's continue. Our dimension, the word dimension, whenever the word dimension comes into your mind, what is dimension trying to tell us? The dimension is trying to tell us that a dimension is a system for representing the fundamental quantity of any quantity at all. A system for representing the fundamental quantity of any quantity at all, using our length, mass, and time, or rather using the fundamental quantity. Also, we could also, in some special cases, the other related fundamental quantity I gave you, like the luminous intensity, the mole, the current, and all those ones, you can also add them to it. But standardly, these are the quantities that are usually common: the mass, length, and the time. That the one is usually common. And our L, the length of the substance, is usually represented as L. Then our mass of substance is represented as M, and our time is represented as T. So dimension is a system whereby we represent any quantity at all by their fundamental quantity, their mass, their length, mass, and time. In cases where we have derived quantities where their mass, length, and time carries a degree in some cases, that system is also the same thing as this, but what we are trying to do at that point in time is to represent them in their mass, length, and time as always. So outside that part, what are the applications of the dimension? What is the major use of the dimension? First of all, our dimension has two major uses. It tells us if a particular formula has already been derived from the standard base. So it can either tell you if a formula is derived. So before you can solve a question, assuming now we know that acceleration is equal to the velocity over the time. Before you can just begin to put your velocity value 2 meters per second divided by our 2 seconds. Before you put this value, you can just use your dimension to check if the this stuff you are trying to do can give you the correct answer you are looking for. Like we already know that our velocity is Lt raised to power minus 1. From this part, Lt raised to power minus 1, Lt raised to power minus 1 divided by the time. So if you solve this part, to now therefore give you Lt raised to power minus 2 for your acceleration. And if you look at the standard form, our acceleration is also Lt raised to power minus 2. So before solving any equation, if you check it physically and confirm it with your dimension, if they interrelate with each other, it already tells you that that equation is already derived. And also it also helps, it can also tell you if a equation is correct or a formula is correct or not. So let's move on. So we're given two equations here. V is equal to U plus AT. Already we know this is our final velocity, this is our initial velocity, and we're told that normally that our velocity is equal to the displacement over time. So velocity is displacement, our velocity normally, we're told normally that our velocity is equal to the displacement over time. So since we already know that our velocity is displacement over time, I'll come here, I'll place L all over T. So I'll come to the other part. C on the same velocity is also equal to L over T, plus our acceleration, we're told that is equal to velocity divided by time. So our velocity we know is L over T, Lt raised to power minus 1. L over T is the same thing as Lt raised to power minus 1. If you are familiar with indices, you can just take your T upward by introducing the minus 1 sign to it. So from there, Lt raised to power minus 1 for the velocity, then the time is T. Then our T normal is also equal to times T. So from here, our T here can cancel this T. So we'll be left with L over T is equal to L over T plus L all over T. So looking at this already, we are having same value here, same value here, same value. This already tells us that this equation is dimensionally correct, and also the equation can be the equation, it also provides an information that tells us that this equation that was given here has already been derived. So that is the point I was trying to raise out there. So let's continue. Then the other formula, x is equal to v over 2a. Our x here is talking about the length, so is L. Then our velocity, Lt raised to power minus 1, like I told you before. The 2 here present is a constant. It does not in any way has any fundamental quantity or a system for representing its fundamental value. So the 2 here is a constant. Whenever you see a constant, Whenever you see 2, just know it's a constant. Any other system that is not a fundamental quantity, know that they are constants. So I'll come to the acceleration. The formula for acceleration is velocity over time, which is Lt raised to power minus 2. So from here, our L can cancel the L. So we'll be left with L is equal to T raised to power minus 1. If this one goes up, it's turn plus 2. We'll now be left with L is equal to T raised to power 1, which is equal to T. And our L is not equal to T. That tells us already that this equation is not in any sense derivable, and the equation is not, the formula rather, is not correct. So that is that under that part. Take note, our dimension cannot tell us if a quantity is physically correct. It can only tell you if a quantity is, dimensionally correct. It cannot tell you if it's physically correct. Example, this formula, x is equal to 80 and x is equal to 80 squared. We know that already that our x is talking about distance, so I can make it L is equal to our acceleration. We know already is Lt raised to power minus 2, then dot t square. This t minus 2 plus 1 will give us, it will now be L is equal to Lt raised to power minus 2 plus 1 from our normal indices. So from there, we already know that our L is equal to, rather, minus 2 plus 2. So it will not be minus 2 plus 2 give you 0, and any t raised to power 0 from indices is what? It will give you 1. So our L is equal to our L here. Take note, this system, the formula is dimensionally correct, but it is not physically correct. This formula, if we try to trace it back to our normal physics, this case only occur in projectile raised at a height. If it is released from this top part at a height, we already know that our velocity is equal to 0, or our initial velocity is equal to 0. We can use our normal motion formula, s equal to ut plus 1 over 2 at squared. At the top of this stuff, our initial velocity is equal to 0. So definitely everything here will be equal to 0. And our x is equal to what? 1 over 2 at squared. So this is where they brought this formula from. Our x is representing the x here, but we're not giving the complete value. So this already tells us that our dimension does not give us the exact formula the way it is. So it only tells you if it is dimensionally correct. So from this expression, we have already seen that, oh, definitely it's dimensionally correct. But from here, it is not physically correct according to our normal formula for solving it. So that is that for that part. So outside that, we have the conversion factors. Conversion factor is a system that we use in converting a particular unit to another unit. So assuming we're told to convert, it's a system we use to convert a particular unit from one unit to another unit. And take note, if you are trying to solve any system converting a particular unit to another unit, the quantity are represented as an algebraic equation, in the sense that they can be multiplied and divide with each other. You must make sure that the system at the left side, equal system at the left side, will cancel the system at the right side also. And we must make sure that a conversion factor in which a number is not present at the front of it, that kind of a conversion factor, we already know that the value is 1 that is present at the front of it. So let's look at this system. We're told to convert 68 kilometers to miles, 648 kilometers to miles rather. And we know that 1 kilometer of any substance, this one is expected to be in your head, is equal to 0.621 miles. So is equal to 0.621 miles. So if I come here, I put my 68 kilometer, 648 kilometer is equal to x mile. So if I cross multiply here, it will now give me our x times 1 kilometer is equal to our 648 kilometer times 0.621 mile. If you look at it, kilometer is present here, kilometer is present here. So this one will cancel out this one. I told you that if there is no term, assuming I remove this one from here before I cancelled it, I wish I remove it. Know that what is present at the front of it is 1. So if the kilometer cancel kilometer, will be left with just mile. So our x will now be equal to 0.62 times 648 kilometer. 0.621 times 648 times 648. It will now give you 0.6 times 648. If you solve it, you have 402 miles as your answer. Instead of undergoing this long stress, I don't like stressing myself. What I usually do is that I will just pick my calculator and solve for this conversion factor. How will I do it? You come to your calculator. First of all, you type, if this is your calculator, what you just do is you first of all write the number 648. 648, you write the number 648. Then how can I convert kilometer to miles? You check the back of your calculator. Usually they usually place it at the back. If you check it very well, where can I convert kilometer to miles? Okay, it's at 8 here. So you write, you type, if you type shift, type the boss shift, and you type the boss convert. If you type shift, you type convert. Then you type number 8, since it's number 8 we are dealing with. So you will find out that it has already arranged. You now say equal to. You see, you find out that the same answer you got here is the same answer you get, which is 402 miles. When I use a calculator, it gave me 402.65 miles, which is the same thing as this. So that is that under the theoretical aspect for physical quantity. The next section I'll be taking you is the aspect that has to do with the calculation aspect on how to calculate for any physical quantity question, derivation and all those stuff. So if you have any question, you can just simply tag it on the comment section, and the rest of the class, or maybe in my next lecture, I could just quickly introduce or solve that part before leaving the class or the lecture we are carrying out. So thank you.